Question 4. You want to identify an unknown object, or two unknown objects. The first one is weighed to be 200 newtons, and when placed in water, it's weighed to be 125.9 newtons. So what's the material of the object? Okay. So we have a situation where you weigh the object on a scale, and we find it to be 200 newtons. Then you do the same thing, but this time in water. And you find it to be 125.9 newtons. So we want to know, what's this object? What material is this object? So let's start with writing an expression for the force of gravity on this object. Well, the force of tension, 200 newtons, must balance the force of gravity. It's not moving. So we can say force of gravity is mass of the object times gravity. And the buoyant force in this situation, our buoyant force is going to be the subtraction of these two. Right? This was 200 newtons in air. We put it in water and it weighs less. So where does that difference come from? Well, it's the buoyant force pushing up on the object. So my buoyant force is going to be the subtraction of these two. Okay. Now we also know the buoyant force is the weight of water that it displaces. What does that mean? Well, the weight is like mass times gravity of the water that it displaces. So the mass of the water displaced times gravity. This number is going to be 200 minus 125.9. It's the difference between these two. Alright. Now, the question is, we want to know about densities. What material is the object? If we know the density of the material, then we know what the material is. So we got to put everything, both of our masses, in terms of densities to solve this problem. Okay. So what's our definition for density? Density, I'm going to write as this letter. Density is mass all over volume. Okay. So let's write this first equation in terms of its density. Mass of the object, well, if I want to get mass all by itself, I have to multiply volume by both sides. So I can write this as density of the object times the volume of the object times gravity. Where here I'm just isolating for mass. That's all I'm doing, and then plugging it into the equation. Over on this side, with our buoyant force equation, mass of the water displaced, exact same, except instead of the object, I'm going to look at water. The density of water times the volume of the water displaced times G. Okay. Now, Archimedes' principle, he was in a bathtub and he noticed that whatever water overflowed from the edge, that must be the volume of the object that he placed in the bathtub. So for example, if you jump in the bathtub and the water is displaced by 3 liters, that means the volume of your body must be 3 liters. So we can say the volume of water displaced must be the volume of the object. Alright. So let's sub in some numbers so it's easier for us right now. Force of gravity, Up at the top, we see that it's 200 newtons. The density of the object, well, that's what we're trying to find. We don't know what the volume of the object is, G. The buoyant force, 200 minus 125.9. It's going to be 74.1 is equal to the density of water is 1 kilogram per liter. The volume of water, we don't know. So let's divide equation 1 by equation 2. Let's divide those two equations. So when we do that, we get 200 divided by 74.1 is equal to look what happens. We can cancel out our velocities and our gravity. We're just left with P naught is equal to 274.1 times 1 kilogram per liter. That's going to be the density of our object. What do we find that to be? Almost 2.67 kilograms per liter, which if you look on your table, looks like it's aluminum. So therefore, the object is aluminum. The object's aluminum. Alright. For the second part of the problem, you have a mystery object that's floating in water. Okay? The water displaces 3.2 liters. So let's kind of draw a picture of what's happening. You've got this object, it's in water, it's floating, and the water level, when placed in water, it goes up 3.2 liters. Now when you take this entire box and push it down into the water, it says it displaces 5 liters. Okay. So if we take this box and push it all the way under the water, this goes up 5 liters. So I can say that the volume of this box must be 5 liters. Volume is equal to 5 liters. As for when it's floating on top of the surface, look back to question 2 or question 3. You'll see that for a floating object, the volume of water it displaces or we can say instead of volume we can say mass, because 1 kilogram of water is equal to 1 liter of water. So the mass of water it displaces is equal to the object's mass. What does this mean? Well, if this number was larger, just say this number was 4 liters, and this object was floating, I would be able to tell that this is a 4 kilogram box. Okay? So as long as it's floating, the value of water that it displaces, the volume of water that it displaces, is going to be the same as its mass. So, its mass is 3.2 kilograms. And the conversion factor I did there was 3.2 liters times water has 1 kilogram per liter. So that's just equal to 3.2 kilograms. So that's the mass of water that it displaces. And because it's floating, that must also be the mass of the object. So we have the mass of the object and the volume of the object. So if I want to know density, it's mass all over volume, which is 3.2 kilograms divided by 5 liters, 0.64 kilograms per liter. If you look on our table, okay, it must be an apple. It has the same density of an apple. Therefore, the object is an apple.